Calculus, video 77, examples of u substitution with definite integrals. So I have three examples here we'll kind of work through of u substitution when we have definite integrals, integrals with bounds. And again, the way you're recognizing should I use u substitution is, do I know how to take the integral of the thing that I have here? If not, consider a u substitution. I don't know how to take the integral of 8x divided by x squared plus 3 cubed. That seems pretty complicated, so probably a u substitution is needed in order to make that integral, that function, simpler so that I can take the integral. So we're going to say let u equal x squared plus 3. The derivative du is 2x dx. Okay, I like that because my derivative of x squared plus 3 is 2x. That is another part of the problem, right? I have 8x in the problem. And so the good thing about that is when I solve for dx here, I get du divided by 2x. And when I replace dx with du divided by 2x, the 8x and 2x cancel or simplify so that I get 4 over 1, right? The x's cancel out. So that's good. I'm also going to change my bounds. If you're a do not change your bounds person, then you won't do this part. But when x equals 3, I get this. I get u is equal to, I'll use this equation here. Let u equal x squared plus 3. So that would be 3 squared plus 3. That's 9 plus 3 is 12. So my upper bound went from an x value of 3 to a u value of 12. And my lower bound goes from an x value of 1 squared plus 3, to a u value of 4. Okay, so I'm going to go ahead, I'm going to change the bounds. I'm going to substitute x squared plus 3 for u, or u for x squared plus 3. And I'm going to substitute dx, I'm going to let that equal du over 2x. It should look something like this. I now have the integral from 4 to 12 instead of 1 to 3. I'm going to leave the 8x. X squared plus 3 becomes u, it was cubed, so it's going to be u now to the third power. And dx becomes du over 2x. X's cancel. 8 divided by 2 is 4, so I'm going to bring that 4 out front. Integral 4 to 12 of 1 over u cubed. That would be the same thing as u to the negative 3 du. Good. So now I have u bounds as I change my bounds to u's, and I have a function in terms of u. So I'm going to integrate this. This is 4 times u to the negative 3. We're going to add 1 to that exponent. That becomes u to the negative 2. Divide that now by my new exponent, negative 2. That's the same as multiplying by negative 1/2. And I will evaluate that from 4 to 12. So we get 4 times negative 1/2. That would be negative 2. U to the negative 2, that would be 1 over u squared, evaluated from 4 to 12. So I get negative 2 times 1 over 12 squared minus 1 over 4 squared, which you could put in the calculator, but let me see if I can go ahead and work this out. That's negative 2 times 1 divided by 144 minus 1 divided by 16. Oh, I'll probably have to have some common denominators here, don't I? Let's see, 16 times 9 is 144, so this is negative 2, 1 over 144 minus 9 over 144. That's negative 2 times negative 8 over 144. That would be 16 over 144. And since earlier we just said that 16 goes into 144 9 times, this would be dividing both by 16. 16 divided by 16, 1. 144 divided by 16, 9. We get an answer of 1/9. So what we're saying is the area under the curve of 8x over x squared plus 3 cubed from 1 to 3 is an area of 1/9. Also, if you do the u substitution, what we find is that the area under the curve, right here is what we'll look at, of 4 times u to the negative third, or 4 divided by u cubed, from 4 to 12 is also 1/9. You don't have to draw these pictures, but let me go ahead and kind of draw the picture out just as we're learning through here. The first function was f of x, this time in terms of x's, 8x over x squared plus 3 cubed. 8x over x squared plus 3 cubed. Okay. A rough sketch of that function looks something like this. Kind of comes out here, goes down, it comes up, and then kind of back down like this. We are evaluating that on the interval from 1 to 3, right? The bounds up here were from 1 to 3. So these are x bounds. So this is my x-axis. This is my f of x function, and it goes from 1 to 3, kind of about right in that region here. And you get an area like this. That's probably zoomed in a bit much, but remember that area is about 1/9. Okay. The function here that I've drawn, when I switch this over to u's, is 4 times u to the negative 3, or 4 times 1 over u cubed. In terms of u, that is g of u is 4 over u cubed, evaluated on the bounds from 4 to 12. From 4 to 12. And that picture, roughly, looks something like this. 1 over u cubed times 4, so we're looking at kind of something like this. And something like this. Now, but instead of an x-axis, it's basically like acting like a u-axis here, and I have y there. This is going from 4 to 12, and so a rough graph is going to say it's that area there. And although the shapes are quite different, the area of each of those regions is the same. Once again, I changed my bounds. 3 and 1, x is 3 and 1, goes to 12 and 4. So because I changed my bounds to u bounds here, I was able to leave my function in terms of u and just plug those u bounds into the u. If you leave your x bounds 1 to 3, if you don't change your bounds, remember, you have to back substitute and replace the u with x squared plus 3 before you plug in your bounds 1 to 3. Okay, very good. Let's try the next one. Number 2. We have the integral from 2 to 3 of x squared over 30 minus x cubed dx. Okay, once again, this looks a little bit complicated just to try and take the integral, probably a u substitution problem. Well, what should your u be? It should be a function, typically, not always, but typically a function whose derivative is also in the problem. In this case, I'm thinking, let's let u equal 30 minus x cubed, that whole denominator there. In which case, then du is negative 3x squared dx, right? Derivative of 30 is 0, derivative of negative x cubed is negative 3x squared dx. Solving for dx, I get du over negative 3x squared. Right. And again, the reason we do u substitution is to try and create a problem that's a little bit easier, right, to integrate. Now, since I'm doing u substitution and I have bounds, I like to change the bounds. I'm going to start off with an upper bound of x equals 3. Using the equation let u equal 30 minus x cubed, u then is equal to 30 minus 3 cubed. 3 cubed 27, 30 minus 27 is 3, I get u equals 3. And sometimes that happens where 3 gets mapped to 3, right? The transformation there is 3 stays put, and when now it's x equals 3 is the same as u equals 3. For my lower bound, I have x equals 2. So I get u equals 30 minus 2 cubed. That would be u equals 30 minus 8. That would be 22. Okay, this is another situation where my lower bound ends up being 22. My upper bound ends up being 3. That's okay. Don't switch them. Don't force 22 to be up top. If 3 map to 3 and 2 map to 22, that's where we put them. And so we get the integral from 22 to 3. We have the x squared we'll substitute 30 minus x cubed, we'll make that a u, and then dx becomes du over negative 3x squared. This is good because the x squareds cancel, and I'm going to bring a negative 1/3 out front since that negative 3 is in the denominator. And we get negative 1/3 integral from 22 to 3 of 1 over u du. And again, convention says we like to have our lower bound be less than our upper bound. So I have a negative 1/3 out front, but even if I did not have a negative 1/3, even if that was positive 1/3, I would go ahead and switch my bounds here to keep that convention of my lower bound being less than my upper bound. However, in this case, it works out great because now when I switch that, instead of going from 22 to 3, lower to upper, I'll go from 3 to 22, that switches the sign, and then instead of a negative 1/3, that's going to create a positive 1/3. So we get positive 1/3 integral from 3 to 22 of 1 over u du. Remembering that I have u bounds, so since I have u bounds, I don't ever have to go back and replace my u's with x's. I can just leave them as u's. This then is 1/3. The integral of 1 over u du is the natural log of the absolute value of u, evaluating from my u bounds 3 to 22. This is 1/3. This is the natural log of the absolute value of 22. That's just 22. The absolute value of 22 is 22. Minus the natural log of the absolute value of 3. Well, the absolute value of 3 is 3. So we have this. Which, by the way, is a fine answer. If you want an exact answer, you could leave it like that. That'd be just fine. You could use properties of logarithms. Remember logarithmic properties, the natural log of a minus the natural log of b. That's the same thing as the natural log of a divided by b. Okay, that's a logarithmic property we have. So we could also say this is equal to 1/3 natural log of 22 over 3. Same answer. Or we could get a decimal. All right, so we could do 1/3 times natural log of 22 minus natural log of 3, or 1/3 times the natural log of 22 over 3, about 0.6, how about that? About 0.664. Approximately 0.664 for a decimal answer there. Okay. Picture, just draw a couple more pictures. We'll stop drawing pictures eventually here. The curve x squared over 30 minus x cubed. All right, the f of x function looks something like this. It comes down, it comes up, and it kind of starts to then kind of go off like this. We were looking from 1 to 3, and so we wanted an area kind of like this. Kind of that region there. This is my f of x equals x squared over, I believe it was 30 minus x cubed on the interval from 1 to 3. We're now switching this from x bounds into u bounds by that equation, let u equal 30 minus x cubed. I'm sorry, that should have been from 2 to 3. From 2 to 3, not 1 to 3. So, something like that. Okay, using that equation, right, if you look at, say, right about here is a great place to look. That transformed into 1/3 times the integral from 3 to 22 of 1 over u. Okay, that looks something like this. 1 over u, and then 1/3 makes it even smaller. It looks like this. These are now a u axis here and a y axis here, going from 3 to 22. 22 is probably way over here. We get this area. Very different looking graphs, very different regions, however, same area. Okay, last one for this video. Number 3. How about the integral from 0 to root 3 over 3 of 2 over 1 plus 9x squared dx. If you want to, you can pause the video, try this one on your own first before continuing. Okay, hopefully you've tried it, but if not, we'll kind of work this together. When you look at this problem, sometimes for all these actually, it's not a bad idea to say, okay, what does this resemble? And what does this look like? Does this look like something that I know? In this case, this kind of looks like it has the same form as like 1 over 1 plus x squared dx. And I know what that integral is. I know that integrates to the inverse tangent of x plus c. This looks a lot like that. My problem though, it's not 1 plus x squared, it's 1 plus 9x squared. And so what I'm thinking here is, okay, this answer should be inverse tangent somehow, but I need to kind of force this 9x squared to not be 9x squared, but to just be some variable squared, like say u squared. If I can make this denominator 1 plus u squared, then I can think I can turn this into an inverse tangent. I can integrate to get to inverse tangent. Okay, so the line of thinking is, okay, if I need 9x squared to be u squared, if 9x squared needs to be u squared, then what I'm thinking here is what squared gives me 9x squared? If I have 3x and I square that, that would be 9x squared. All right, so what I'm thinking is, instead of 1 plus 9x squared, think of it like this. Think 0 root 3 over 3 to 1 plus parentheses 3x that's being squared. So if I can just let u equal 3x, then when I do the substitution, I'll have 1 plus u squared. And that's what I'm looking for. So if you see one of these problems where it looks like an inverse tangent, or that looks like an inverse sine, or that looks like an inverse secant, but instead of, say, just x squared, you have 9x squared, or 16x squared, or 25x squared, think about doing this, where you're thinking about what would make that just be u squared there. Well, if that was 3x, and I squared it, I'd have 9x squared. So what we're going to do is kind of think about that as 9x squared as 3x, quantity being squared, and I'm going to let u equal that 3x. Then du is 3 dx, the derivative of 3x is 3. Solving for dx, I get du over 3. And I'm going to do all that substitution, but I'm also going to change my bounds. And I'm going to change my bounds based on the statement, let u equal 3x. My first bound, my top one, is root 3 over 3. My x bound of root 3 over 3. That means u is 3 times that, which is just root 3. So an x bound of root 3 over 3 became a u bound of root 3. An x bound of 0 becomes a u bound of 3 times 0, which is just 0. So 0 stayed at 0. So I'm going to change my bounds to 0 and root 3. And I'm going to do all of the substitution. So those are my u bounds now, right? X bounds have now become u bounds. The 2 is just going to hang out. This becomes 1 plus u is 3x, so this is 1 plus u squared. You know what I forgot the whole time here was my dx that should have been there. My apologies. Dx is du over 3, so I get du over 3. And now I have everything in terms of u's, and I have u bounds. So this is 2/3, bring that 2/3 out front. Integral from 0 to root 3 of 2 is already out front, 1 over 1 plus u squared du. And even though it's a different variable, it's u's and not x's, this is exactly the integral of 1 over 1 plus u squared is the inverse tangent of u. So I get 2/3 inverse tangent of u, not x, but u, from 0 to root 3. Okay, because I have u bounds here, tangent u, I can just go ahead and do the fundamental thermal calculus, do my f of b minus f of a. I don't have to switch back to x's. But if you did not change your bound, you would now switch back to x's. You would let u equal the 3x and then plug in your x bounds. I get 2/3. Then I have the inverse tangent of root 3 minus the inverse tangent of 0. And hopefully you remember your trigonometry. The inverse tangent of root 3, that would be pi over 3, because the tangent of pi over 3 is root 3. And the inverse tangent of 0 is 0, because tangent of 0 is 0. And multiplying that through, I get 2 pi over 9. All right, very good. Maybe one more graph, one more picture here. So 2 over 1 plus 9x squared. It's not a bad idea just to see some of these graphs anyway. F of x is 2 over 1 plus 9x squared. If x is 0, okay, so if x is 0, that term goes away. You get 2 over 1 is 2. So if x is 0, we're up here at 2. If x gets really big, like x is 100, right? What's happening is the denominator gets really big. 2 divided by really big goes to 0, and you get something that kind of curves down this way, and same thing on this side. And what we wanted to do for our bounds here was from 0 to root 3 over 3. Okay, and so we have from 0 to root 3 over 3, the area under that curve looks something like this. Now, when I switched over to u's, right, this was x, now I have u. The function became, right here, 2/3 times the inverse tangent of u. Okay, 2/3 inverse tangent of u. Inverse tangent, remember, has horizontal asymptotes at negative pi over 2 and pi over 2. And it looks something like this. Times 2/3, so it's a little bit squatter, a little bit more towards the u-axis here. And so this curve here is g of u equals 2/3 inverse tangent of u. And I'm going to look at this on 0 to root 3. So from 0 to, say, root 3. And it's that area. And although they're different graphs, different functions, different bounds, you get the same area either way.